Welcome you back for the third video lecture on the measurement of high currents. This video lecture deals with the resistive shunts with advanced designs for measurement of high impulse currents. Coming to the recap, in the last two videos we have discussed about Hall generators for the measurement of high DC currents, current transformers for the measurement of high AC currents. We have gone through magnetic measurements like Rogowski's coil and the magnetic links for the measurement of high impulse currents. And in this particular video lecture, I hope by the end of this video lecture, you will be able to explain the different designs of resistive shunts that are used to measure high impulse currents. The operating principle is very similar to that of your resistive shunts, which we have employed for our normal currents in our electrical measurements course. What we need is nothing but a low ohmic pure resistive shunt. We do require a very low ohmic pure resistive shunt, and the current through the resistive elements, it produces a voltage drop. Let us suppose this is a resistive shunt. R indicates your resistive shunt. The voltage which is being, let us suppose this I is the current which you are want to measure. This is to be passed through this specially designed R. This is your resistive shunt. So I want to measure this I. So first of all, I am allowing it to pass through this R, very small value of resistance, which does not create a major voltage drop and does not hinder your circuit. So a current I into a small resistance R. The voltage which will be developed across this one will be V is equal to I into R. V of t is equal to R into I of t, the instantaneous values. This voltage which is being developed here, it is transmitted to a CRO, this is CRO, through some coaxial cable with surge impedance Z0. And make sure that you terminate this cable with the resistance whose value is equal to Z0, such that there are no reflections. So it is nothing but you are protecting your CRO and directly connecting here. You are using this coaxial cable here. So resistive shunt, the voltage is being measured by your CRO and the signal is being transmitted through your coaxial cable, which is terminated by your resistance with the resistance value Z0. So four important parts: your basic resistive shunt, your coaxial cable, your terminating resistance, and a CRO for measuring the voltage. So the major features of the resistive elements now, we are more concerned the coaxial cable and the terminating resistance and CRO are the common things which we do employ, which we can easily find in the market. The conventional designs we can employ. The only special design is about this resistive shunt, which we are supposed to carefully design such that it does not create a major voltage drop and it is not being affected by some external factors. And now see here, the resistance elements, because of their large dimensions, most of the times, they do exhibit LNC, which we do neglect in case of DC measurements. But in case of AC and impulse measurements, we are supposed to count this LNC also. So this LNC will be represented in this format. See here. This was the original R, but it is having a stray inductance and a stray capacitance. LNC, which will be represented by this one. This is the equivalent circuit of the shunt. So at low frequencies, L can be neglected. See here, the impedance offered by L is omega L, but whereas the C, it is 1 by omega C. See, at lower frequencies, omega L will be very low, so you can neglect it. But at higher frequencies, omega L will be having considerable value. Similarly, the value of C, it will be higher. The impedance offered by this C will be higher at lower frequencies and it will be lower at higher frequencies. So you are supposed to consider this LNC impact also when you are counting this R value. So when the frequencies are somewhere around 1 megahertz or so, these LNC, they will be showing their significant impacts on the measurements. So the normal resistance value, it will be varying, it will be very, very small as been mentioned earlier. It will be in the order of few microohms to some milliohms, and the voltage drop will be very, very low. It will be some few volts. And the value of the resistance, it will be determined by its thermal capacity and heat dissipation of the shunt, because it is being carrying some kiloamperes of current. So make sure that it is having proper heat dissipation. Now, the voltage drop across the shunt in the complex frequency domain may be written as, you can take the equivalent circuit of all this R, let's say. So this is your Vs. If L and C are not present, it was just Vs is equal to R into I of S. But since L and C are present, this is a complex equation now. Now, if C can be neglected, at least, so this equation can be represented as V of S is equal to R plus Ls into I of S. So that's why make sure that you try to make your circuit such that it has very small value of inductance and capacitances. The stray inductance and capacitance should be very, very small. But at least try to make that stray capacitance will be very, very low in order to have a better frequency response. So keeping that in view, we do have different designs in the market. These three are the commonly employed designs. One is a bifilar flat strip design. The second one is coaxial tube design, also called as a park shunt. And the last one is a squirrel cage design. We will just have a look at the design features of these resistive shunts. Now, see here, this is a bifilar flat strip resistive element. See here. First, we will discuss the operation, then we can see this one in the figure. See here, bifilar strip shunts. It consists of the resistor elements wound in opposite directions and folded back with both ends insulated by Teflon or any other high quality insulation. And the voltage signal is being picked up by some UHV connector. See here. Once again, the bifilar design consists of resistor elements wound in opposite directions and folded back with both ends being insulated by some high quality insulating material. See, this is your third one. This is your bifilar strip design, if you carefully see. 3 is your bifilar strip design. So which means that your shunt, this is a complete shunt. 1 and 3, they form your shunt. 1 is your metal base to which these terminals will be connected. See, 2 are the current terminals. 2 indicate the current terminals, C1 and C2. 1 is a metal base to which your material is being connected, bifilar strip. And see here, the voltage, it is to be measured, right? This will be measured with the help of your coaxial UHF connector. It will be having P1, P2 points. See here, this point is P1 and this point is P2. So current flows through in this fashion, see here, through 1, through 3, and it will be moving out. And voltage will be measured at these two terminals. And it will be sent to your CRO using this coaxial UHF connector. Here your coaxial cable will be connected and it will be transmitted to your CRO. See, this is a connection point. This is C1 and C2, and here P1 and P2, these are represented like this, and this is the cable here. So the only specific design is that the resistor elements are wound in opposite directions and folded back with both ends insulated by Teflon or any other high quality insulation. Now, this particular design is very rarely employed because it suffers from a large value of stray inductance. So that's why to overcome this one, we are employing coaxial shunts. We will see now how a coaxial shunt will be. Coaxial shunt will be just like you take two tubes. This is one tube, this is the other one tube. Two tubes. Now, if you carefully see, this is nothing but coaxial tubular design. Now, see, the one is the resistor element. See here, this is a cross sectional view. 2 is the resistive element, whereas 3 is the return conductor. So this is one tube. 2 makes one tube, internal tube. 3 makes a outer tube basically. So the current is passed through this 2 and it is made to come back to the original point through 3. And the voltage terminals will be measured at 2. See here now. In the coaxial design, the current is made to enter through an inner cylinder or resistive element, what we termed as 2 here. And it is made to return through an outer conducting cylinder of copper or brass. See, this is your inner one, this is your outer one. So current which is coming here through 1, these are the current terminals. It enters this cylinder, comes back to the original points again through this return conductor. And this is your potential pickup points. So current is flowing from here to here and it is coming back here. So this is one point of entering the resistive element, this is leaving the resistive element. So this is the potential led. These two are the potential points. So this is one point, this is another point. So here the potential terminals P1, P2 will be there. This is your UHF coaxial current. So the voltage drop across a resistive element is measured between the potential pickup point and the outer case. And the space between the inner and outer cylinder is air, and hence it acts as a natural insulator or pure insulator. So with this construction, there is a quick response of some few nanoseconds or so. We can easily measure the current, and there is a very good higher upper frequency limits. And these are basically employed for the currents which do have a peak value of somewhere around 500 kiloamperes or so. Extensively used designs, sparks shunt designs for measurement of high impulse currents. Now, okay, the next one is your squirrel cage shunts. This is the third one, squirrel cage shunts, where the design will be just like your squirrel cage induction motor. See, particularly these are employed particularly during post arc current measurements, or whenever the sparks have already come, we need to know what is the amount of current which is flowing, which has already flown. Then in that sort of applications, we will be employing the squirrel cage shunts. So during this post arc current measurements, because of the arcs which are being created there will be huge amount of energy which you are supposed to dissipate. So you do need these ohmic valuations which can dissipate larger amount of energy, which are resulted because of the higher currents which are developed there. So in such cases, tubular shunts may not work out because of their limitations in their heat transfer capability. So in that case, squirrel cage shunts are designed. Those are also just like your tubular structures, coaxial structures. The resistive cylinder is replaced by thick rods or strips. See, and the structure resembles like rotor construction of a double squirrel cage induction motor. See, instead of, see, in this one, what you are using is, you are using a small cylinder here in coaxial arrangement of ohmic shunts. Now, in this case, what you are doing is nothing but the same structure, the same figure. The thin cylinders, they will be replaced by your thick rods or strips. And just, it will be just like your inner thick cylinder, outer is also a thick conductor material, thick conducting cylinder. So it just looks like your squirrel cage induction motor, double cage squirrel cage induction motor. So the equivalent circuit is similar to that of squirrel cage construction, and it will be different from that of your coaxial tubular shunt or park shunt. It will be a little bit complex. And there is a separate compensation technique which is required for this squirrel cage shunts, and this is your compensating network. They may ask you for 1 mark or 2 marks to draw the compensating network for squirrel cage shunts. You can draw this one. So that's it regarding your resistive shunts. A quick review. There are 3 different designs. Normally resistive shunts are employed for the measurement of high currents. Particularly when you are employing for high impulse currents, these resistances, they will show the values of ILNC. They must be neglected. They must be minimized. To overcome that things, we are having special designs. 1, 2 and 3. The first one is bipolar strip designs, the second one is pack shunt, the third one is